Hey students, we're going to talk about pH scale and the calculations that go with it. And this is a very important discussion for your biology classes. So we were talking about acids and bases. So let's picture water. Now water is an interesting substance because of many reasons, as we've seen in the semester. But in this case, it's because it can act as an acid and a base. And what it does is it reacts with itself. And this is called self-ionization reaction. So one water molecule donates H plus to the other one. So let's look at it from a Lewis dot perspective. So here's one water, and here's another. What'll happen is this bond breaks to form the H plus, and the other one accepts it via its lone pair here. And what you end up forming is H3O plus and hydroxide. So H3O plus is hydronium and hydroxide, OH minus. Okay, so this reaction is what's called an equilibrium. Equilibrium is the idea that a reaction goes forward and then it can go back, and then at some point, the speed or rate at which it goes forwards equals the rate or speed it goes backwards, and then you reach what's called an equilibrium reaction. In this case, when the rate going forward equals the rate going reverse, you end up with a reaction that has a huge number, a very small number of ions. So for sure, when this reaction goes forward and backwards, the amount of ions is very small. Now, we can describe the amount of ions through a math equation, which is hydronium ion times hydroxide is given by a constant, which is called Kw, and that has a value of 1.0 times 10 to the negative 14. So this K is called an equilibrium constant. And that K only includes the aqueous, the ions here. It does not include the liquids. And that's because they are in very large amounts, and they are in a pure substance form, so they're not included in K. Now, we didn't do the whole chapter on this idea, so some of this is just going to have to kind of, I guess in a way, take my word for it, because we didn't do the whole chapter or any chapter on the equilibrium part. So just kind of introducing it here in a very introductory level. Okay, so when we look at this, this is going to be a very important equation for you guys. H3O plus times hydroxide equals 1.0 times 10 to the negative 14. Now, for a neutral solution, which we're describing because we just have water, right? This is just water. If you notice the mole ratio here, 1 to 1, right? 1 mole hydronium and 1 mole hydroxide. So these guys end up being equal to each other. And if you think about what number multiplied by itself would give us 1.0 times 10 to the negative 14, that number is 1.0 times 10 to the minus 7 molar. So this is the definition of neutral. That hydronium and hydroxide equal 1.0 times 10 to the negative 7 molar, and that they are equal to each other. Okay, so that's here, and I'm going to put the brackets. And just a reminder, what the brackets meant is the brackets equal molarity. So that's our concentration. Okay, so when those are equal, the solution is neutral, and that's 1.0 times 10 to the negative 7 molar for each of those. Okay, now you put an acid into the solution. Picture that you have our easiest acid, which is HCl. That HCl plus water. Acids make H3O plus, and then in this case, the remaining one is chloride ion. So do you notice how the H3O plus goes up when you put an acid into water? So let me highlight that. So this is increasing. Now, if your Kw okay, so there's our Kw equals hydronium times hydroxide. Now notice what will happen is if we increase this number, hydroxide has to go down to maintain this constant. Now, if you can't see it with this number, let me give you an easier example. If I have 5 times 3 equals 15, if I change the 5 to a 15 and I want to maintain that number 15, the 3 has to go down to a 1. So if this one goes up, this one goes down. So that's what we're seeing here. Hydronium goes up, hydroxide has to go down to maintain the constant. Okay, now let's think about a basic solution. Let's say you have NaOH as a base. Okay, bases are going to increase hydroxide. So if I write this out here, if we increase hydroxide, hydronium has to go down, the concentration. Okay, so this is always true. If hydronium goes up, hydroxide goes down. If hydroxide goes up, hydronium goes down. And this is a great graphic to show that. And I would take a look at this real carefully. In a neutral solution, they're equal. In an acidic solution, hydronium goes up, hydroxide goes down to maintain the constant. In a basic solution, hydroxide goes up, hydronium goes down to maintain that constant. Okay, I would like you, once I'm done talking, I'd like you to take out your calculator. If you could, you can pause me to get it. I want to show you something that's important here, that if Kw equals hydroxide times hydronium, okay, then we can solve for hydronium. Hydronium will equal Kw divided by hydroxide. And then hydroxide will equal Kw divided by hydronium. So what I'd like you to do is to take your calculators and confirm this with all the numbers on this slide. So for example, you're going to take hydronium, take the second one, hydronium, 1.0 times 10 to the minus 2, and multiply it by 1.0 times 10 to the negative 12, and make sure that you get this Kw value. And then I'd like you to do, let's say, this one here. Take the Kw and divide it by hydronium and make sure you get that hydroxide number. So this will be a very good calculator practice to make sure that you are getting the correct numbers that you need to. So you can pause me and do that, and then I'll keep going. This is saying it the way, this is the same thing I just wrote up. And then we can practice on this one as well if you'd like. What is H3O plus if hydroxide is this? So H3O plus will equal Kw divided by the hydroxide concentration. So take a moment to calculate that number in your calculator. Pause me. And then this is showing the same setup. And here's the same setup. You should have gotten 2.0 times 10 to the negative 7 molar. Okay, so pH scale is a really important scale. And it's going to tell us the acidity of a solution, and it's usually ranged from 0 to 14. And we're going to look a little more closely at this now. But what I want you to think about is, what are the numbers trying to tell us? So acidic solutions, and let me put it here kind of as a number line maybe. So you have neutral has an H3O plus concentration of 1.0 times 10 to the negative 7, and that equals the hydroxide. Okay, so acidic solutions will have hydronium that are greater than this number. So that would be like 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, bigger. Those will be acidic. And then basic solutions will have hydronium less than that. So like 10 to the minus 8, 10 to the minus 9. Okay. And then neutral will have them equal. We're going to learn how to calculate pH, but for right now, pH is going to be anything less than 7 will be acidic. Anything greater than 7 will be basic. So let's test this out. If HCl has a pH of 1.5, that pH is less than 7, so that would make it an acid solution. The pancreas fluids have a hydronium concentration of 10 to the minus 8. Going back to my previous slide, if you notice, if 10 to the minus 8 is less than 10 to the minus 7, so that's going to put that guy into a basic solution. Okay, so that's basic. A soft drink is pH 3, so that's pH less than 7, so that is acidic. pH 7 is neutral. Let's go to the F first. 5 times 10 to the negative 12, that's much less than 10 to the minus 7. So that is basic. And then now the hydroxide one is interesting. One way to easily think of this one or to do is to convert it over to hydronium. So you're going to have hydronium is 1.0 times 10 to the negative 14. Then you're going to divide by that number, and what you're going to get is a number that is going to have, back on our chart, it's going to have a H plus that's bigger than 10 to the minus 7. So that's going to make that guy acidic. Okay, another way of thinking of this one is that this is a very, very small hydroxide that's going to make the H3O plus very big, and that's going to make that acidic. Okay. Let's talk about pH scale now. pH is defined as negative log of hydronium. And a couple comments. There's also a pOH that is negative log of hydroxide. And so, first of all, we have to ask the question, what the heck is a log? A log is a logarithm, and that means base 10. So let me show you some easier numbers, and then we'll flip it over to this. The log of 100 is 2 because 10 to the 2 equals 100. The log of 1,000 equals 3 because 10 to the 3 equals 1,000. The log of 0.1 equals -1. That's because 10 to the -1 equals 0.1. You can plug those into your calculator to confirm that. Okay, 10 to the -1 is the same as 1 over 10. So what we're looking at here then is a logarithm is a way of converting a number to an easier to deal with number when it comes to our very dilute acid solutions. Now let me get back to that because you're probably still pondering the logarithm business here. One other thing I should say is that this here is called an anti-log. And all of this is on your calculators. It'll show a log key, and then there'll be a 10 to the x key. That's your anti-log key, and that's a second function key. Now, that's going to be the case on 99% of the calculators. If you have any questions on how to use your calculators, please come see me before class or stay after class to ask. Okay, so a logarithm is base 10. So a log of 100 equals 2 because 10 to the 2 equals 100. Okay, now following that line of thought, let's come back up to our pH and pOH values. So if we have, in general terms, let me put this in general terms, the log of y equals x because 10 to the x equals y. So applying that here, I'm going to call pH x and hydronium y. Y, H3O plus, equals 10 to the pH. But if you notice, there's a negative sign there, so that's going to go there. Hydroxide equals, okay, let's apply that here. X equals negative log of y. So y equals 10 to the negative pOH. So the hydronium and the hydroxide are actually, when we solve for them, we are taking the antilog. Okay, now one other very important relationship that we'll see later is that, and I don't want to derive it because I don't want to confuse you too much, but H3O plus times hydroxide equals 1.0 times 10 to the negative 14. I could do some algebra and take the log of both sides and rearrange. And ultimately, when I do that, when I take the log of everything, I'll end up with a relationship where pH equals pH plus pOH equals 14. So I would definitely know this. I don't think I need to derive it for you because I don't want to confuse more. So I'm going to highlight, if I can, let's see if I can. I want to highlight the important relationships that you're going to need. So you're going to need this one, the anti-log. So I'm highlighting them, and these would all be given to you on a quiz or test. And then this one. Okay, and then let me know if you need help on your calculators. Okay, so take a moment to write those down, and then we're going to use them to just solve different problems with pH and hydronium. Okay, and then the other important thing again is that if we increase hydronium, we decrease hydroxide. And that's because, oh, I didn't highlight this other one. I should have. Hydronium times hydroxide equals Kw. Okay, so if one goes up, the other one goes down. Okay, so let's do some calculations. Here's a logarithm. And so pH is negative log of hydronium. So take a moment. If you have a hydronium of 1.0 times 10 to the negative 4, and you put that concentration in, pH will equal 4. So make sure that you know that this works out for you on your calculators. So practice that. And then the other thing I mentioned to you, or should mention to you, is that if this has 2 sig figs, our pH will have 2 decimal places. And so the reality here is that our pHs normally have 2 decimal places. It's really unusual to see them with less than 2 decimal places. Okay, so double check that guy on your calculator. Here's another one. So practice this one. If your hydronium is 2.4 times 10 to the negative 8, take the negative log of that. And make sure that you double check that you get pH 7.62. Okay, let's try this one. What's the pH of a solution? This is aspirin, which is an acid. It's called acetylsalicylic acid. And it's an anti-inflammatory drug and used to alleviate pain and fever. And so we have the hydronium concentration there. So I'm going to ask the question, what's the pH? So we're going to take the negative log of that number. So go ahead and plug that number into your calculator. And I'm going to click on this, showing the setup here. And this one here is something we did talk about in class, which was how to plug in 1.7 times 10 to the negative 3. We've been working on that the entire semester, but if you are still struggling, please see me. So you take 1.7 in your EE or EXP key, press 3, and then change its sign. Now, this is general, right? This may not work in your particular calculator, but most operate this way. And when you do that, you should end up with pH 2.77, 2 decimal places. So you'd round that big long number to 2.77. So the POH scale is similar to the pH scale. I'm sorry if it got loud. My family's making coffee right now. So it just got very loud in here all of a sudden. So the POH scale is similar to pH, except you're using hydroxide. So pH equals negative log of OH minus. And then pH plus POH is 14. So if you know one, you can find the other. So in this case, if you have a pH of 3.50, the POH would be 14 minus that. Okay, a couple of very important things is that you need to realize, let me highlight this. Here's our neutral scenario. Oops, not doing a good job highlighting that. So there's our neutral. Actually, let me erase that. That did not work out. Okay, so our neutral, I'm going to try again. So our is pH 7. That's where you have a hydronium of 10 to the minus 7. And I want to show you some things here on this chart. Okay, so on this chart, let's talk. So let's start with that neutral. If you take the pH is negative log of 1.0 times 10 to the minus 7, that equals a pH of 7. Okay. And then if you notice, POH is negative log of 1.0 times 10 to the negative 7. They didn't show the 1.0. Those are going to be the same, the same as just saying 10 to the minus 7. And then that's going to equal 7. And then do you notice how pH plus POH equals 14? And then the other thing is that hydronium equals 10 to the negative pH, and hydroxide equals antilog, right? 10 to the negative POH. So let's take a look how you can kind of practice if you can understand these guys. So let's just take a random one. Let me highlight pH 4. Okay, I would prefer it with more decimal places, like 4.00, but this is just trying to keep things more simple. So if I have a pH of 4 and I want to know, hey, what's the hydronium? I would come up to this equation. Hydronium is 10 to the negative pH. So do you notice how hydronium is 10 to the negative 4? Okay, let's do something else here. If I know I have a pH of 4, what's the POH? Well, 4 plus 10 equals 14, right? So that's why my POH is 10. And then if I want to know what the hydroxide is, hydroxide will be 10 to the negative POH. So that's 10 to the negative 10. Okay, so go ahead and kind of reason that out with a lot of these, and then you'll get a good feeling for how all the relationships are interrelated, and also a better feeling for what antilog means. This part here, right? That's the antilog. Okay, now there's another important piece on this chart. I'm going to erase those so that they're not confusing us. Okay, so here's the deal. You have the idea that here's our neutral, right? This is our neutral. When you increase hydronium, so you see how these are getting bigger, these numbers are getting bigger, you're getting acidic. The hydroxide is getting smaller. As we said, those are always inverse to each other. The pH is less than 7 and the POH gets bigger. So in an acidic solution, POH is less than 7. I'm sorry, pH is less than 7 and POH is greater than 7. So these are our acidic solutions. The other thing that I'd like you to notice is that when the pH changes by 1 pH unit, the concentration of hydronium goes up 10 times. So 1 pH unit is a 10-fold change in hydronium. Okay, for basic solutions, basic sees a decrease in H3O plus and therefore sees an increase in hydroxide. Now my arrow there is going to be a little bit confusing, so let me erase that arrow. And I'll just put increased hydroxide. How's that? I'll get rid of these. And I'll just look at the arrows I've shown there for hydronium. Okay, so you see how the hydroxide's increasing. And what that's going to do is an increase in hydroxide is a decrease in pOH. A decrease in hydronium is an increase in pH. And once again, if we change the pH by 1 unit, that is a change tenfold in hydronium, in this case, decreasing tenfold. Okay, in the next few slides, what I'd like you to do is just read them over and work on the problems that are on here. I won't go through them. They'll be, the solutions will be given to you on the PowerPoint. I just want to wrap up by looking at the pH of common substances, because I think it's important to have a good feel for this. You look up at the top, a 1 molar HCl has a pH of 0, and I do want to highlight something on that, is that the pH scale is useful for dilute acids and bases, meaning that the molarities that it mostly references are between 10 to the negative 1 and 10 to the negative 14. And so that's the range that you get a pH of 1 to 14. There are acids that are super concentrated. So if I have like a 12 molar HCl, that means 12 molar H3O plus. Well, if you plug that into your calculators, you're going to get a negative number. And that's therefore not the point of this. If I have a 12 molar HCl, I know it's a concentrated acid. I don't need pH scale to help me out. pH scale is useful when their numbers are small, 10 to the minus 5, 10 to the minus 8. That's when it becomes a useful tool. So for a 12 molar HCl, pH scale is not needed. Okay, gastric juices are 1.6, lemon juice is pH 2.2, vinegars 2.8, carbonated beverages around 3, and orange 3.5, coffee at a 5. Okay, what I want you to notice is that our taste buds appreciate acidic food. So a lot of the food that we eat has acidic properties to it. Do you see how bread 5.5, milk 6.4? So tomatoes 4.2. So you're getting the point that our taste buds have a positive reaction to slightly acidic solutions. Not concentrated like in the 12 molar, right? That would create a severe chemical burn. But these are dilute solutions. Dilute, again, meaning molarities that are small. So these are molarities that I was referencing. Okay, neutral, pure water, 7. Drinking water tends to be a little bit basic. Blood, this is an important pH that we talked about, how we regulate that value through breathing. And then detergents tend to be a little basic. Seawater tends to be basic. This is the idea that we're going to be changing the pH, right, through ocean acidification. This has a value of 8.5. I had given you a value of 8.1. And it is a range because it's not throughout the planet. It's not all equally the same at every single spot right around the globe as far as ocean water goes. Household cleanser ammonia, pH 11. 1 molar sodium hydroxide, very basic, something like the Drano that we talked about. So, and So anyways, I like this for you to understand that we have a lot of things around us that fall into this pH scale that we've talked about.